Okay, we'll go ahead and get started. We're continuing our discussion on mass spectrometry. And it's the lead into these analytical techniques that are going to tell us structural information about compounds. So one of the key things on this slide is we know that the molecules all have carbon and hydrogen. The ambiguity lies in if there are other heteroatoms. And again, those are listed in the molecular formula after the C and H count. So the problem that we're looking at is testosterone. So this is a thought experiment. We know what the structure is. We can count carbons, hydrogens, oxygens, determine the molecular formula from that. But we're looking at the data itself to see if we can arrive at that same molecular formula using some of these techniques. And part of this thought experiment is we're operating under this assumption that we're focused on oxygen. And so the reason for that, as I'll show you on the actual mass spec of testosterone, there's clues that are there, and there are these small details that we have to recognize and develop the intuition to rule out other heteroatoms. So the reason we want to sort of, be free in our thinking here is we're going to learn reactions with certain functional groups and conditions, and then we'll know what heteroatoms are there. So it narrows this process down a little bit. But we still want to, be able to look from all angles of attack. And so the lead in from mass spec into the next technique that we'll get to today, IR. IR is going to help us increase our confidence of oxygen being present, and then some other heteroatoms as well. So as we progress through mass spec into IR, basically what we are looking for is the presence or absence of heteroatoms. And the IR part later today will tell us what functional groups are present. But again, if we know the name of a functional group like carboxylic acid, we know it has to have the elements of CO2H. So we know that little bonding pattern, but overall we don't know the molecular connectivity. And so once we get through IR, then we look at NMR, and that tells us exactly how everything is bonded. So why are we using this? We want to, again, figure out what heteroatoms are there. And there's a lot of little subtleties into these diagnostic signals that we have to recognize. And again, I know that the majority of you, 99.99%, maybe one of you might become an organic chemist if I can persuade you, are going into other fields. So the learning skill here is, if you're given some data, can you make sense of that data? Do you see the trends? Whatever you go into, you're going to have to process and analyze data. So as I'll show you on the next slide, based on just some of the numbers present, we can rule out some of these heteroatoms listed. Really, the only ambiguity is the presence of oxygen and fluorine. We know fluorine's not in testosterone, so in our thought experiment, we're not going to consider it. But we can detect fluorine directly through NMR. We maybe won't cover that exactly in this module, but you can detect that directly. So we're making this assumption that oxygen is going to be the other heteroatom. And once we have a working molecular formula, we can calculate degrees of unsaturation. And then as we go into IR, we can maybe assign what some of those degrees of unsaturation are. Are they pi bonds? Are they rings? And then from all of this stuff, we're going to create a working structure. And what we want to do with all this data is increase our confidence of our claim. So that's how lawyers speak. If you've ever interacted with a lawyer for any reason, I worked in a pharmaceutical company and we were writing patents. And the lawyers come in and say, well, we need to unambiguously assign this structure so that it can be defended against any claims against it. So you want to make a watertight case for anything you're proposing. So here's the mass spec of testosterone again, and I've written some stuff on here that I want to go through to show you what the numbers are telling you. So visually, there's the structure. We can do the carbon, the H, the oxygen count to arrive at this molecular formula. From that, we can calculate a mass, 288. But if we're just given this data, what is the data telling us if we didn't know the structure or the molecular formula? The parent ion with this nomenclature M+, the plus means it's a cation that's detected, is at a mass of 288. Beyond that, you see these smaller signals. So anything beyond that, we would say M+1, it's one more mass unit, or two more M+2. And that data is listed here, and I've highlighted those in red, blue, and green. The 288, that's your M, that's the parent. 289, that's M+1. 290 is M+2. We saw that with chlorine and bromine due to their isotope abundances. They had certain ratios of M to M+2. So I want to be very clear when I say for chlorine and bromine, it's whatever the parent is plus 2. See this ratio here, 2%? Again, that's telling you the abundance of how much that ion is produced. Notice it's only 2%. It's not 100% and 100%, 100%, or 30%. That percent right there tells us that chlorine and bromine cannot be present because that ratio would then be different. The parent ion itself, as I've highlighted in yellow, is an even number. So that's saying no odd number of nitrogens can be present. So in one sense, we can rule out nitrogen, but in another, we can't, because if there was an even number of nitrogens, then the mass could still be even. So moving through this as we're contracting what heteroatoms could be present, we're going to take out N, Cl, and Br. So let me write that note. So no odd number of nitrogens present. And finally, there's no real signal at 127, which would be indicative of I plus. And if we do the math, 288 minus 127, I think that came out to like 164 or something. There's no real strong signal that would also indicate an ion that lost iodine. So that funnels us down into the other thing has to be oxygen. So our question is, given that mass of 288, we use the even number to rule out the odd number of nitrogens present. We use the percents of the M+2 to rule out bromine and chlorine. Can we calculate that formula exactly? And the answer, I think, is yes, as we'll see. So here's the blurb about N, chlorine, and bromine. We know C and H are present. We're going to figure out oxygen, how many there are. And in the prior sort of exercise on Monday, we're using the atomic mass of carbon being 12 to determine what is the upper limit of the carbon count. The equation that's shown here gives you the exact number of carbons. And the reason this works is because of the natural isotope abundances of C12 to C13. It's 98.9 to 107, or basically 98.9 to 1.1. And so in this equation where it says M+1 and M, these are the percents, those abundances. These are not masses. So when you have the data and you're shoving numbers in there, you're not putting a mass in there, you're putting the relative abundance of the M+1 to M. And why can we do that? Again, because the C13 is present naturally in that 1.1% abundance. And that's where this 1.1 comes from. So again, I've made the data a little bit easier to figure out here. These are those percent abundances. The parent is 100%. M+1 is 20.5. So you put 20.5 divided by 100, divide all that by 1.1. And why is this telling us the exact number of carbons? Again, it's due to that C12 to C13 ratio. So when you do that, what number do you get? I guess we need to multiply that again then by 100. So 18.6. So you might have some questions. Do I use 18? Do I use 19? Do I round? And I don't want to be flippant, but what you should do is, if you're ever in doubt, just run the scenarios for both numbers. And one practical skill I can tell you to develop is learn how to use Excel. If you don't know how to use Excel, any sort of calculation you can do, you can stick it into Excel, just plug numbers in it, and it'll output things for you much faster than doing it manually. So we got 18. Yeah, so this should say, I shouldn't say max, I should say exact. in a sense, I guess they could be the same thing. 6, we're gonna take 19 as the number.
What does that percent represent?
So the parent ion was 288. We just found that there's 19 carbons. So of that 288, how much of that is from carbon? So 228 of the 288 is carbon. So everything remaining is going to be hydrogen plus the heteroatom. So again, by using that formula, again, the percents, not the masses, that allows us to calculate the exact number of carbons present. We can then figure out the mass contribution of carbon, and then we're narrowing it down to what are the ratios of hydrogen to anything that's remaining. So we have 19 carbons. For 19 carbons, what's the maximum number of hydrogens that can be present?
40.
So we use that formula for the alkane. So I think I heard someone say 40. So the hydrogen contribution could be up to 40. So if we subtract out the 228 for C, the 40 for H, what do we have left over? $20? So what that's telling you is we figured out from the maximum exact number of carbons, the maximum number of hydrogens, there's still some mass left over that's unaccounted for. So 20 is a weird number in the sense that it doesn't match the atomic mass of any heteroatom exactly. Fluorine is close, but it's 19. So we can't shove a fluorine in there because then we'd have to add an extra hydrogen to make up the difference of 20 minus 19 of 1. But we're already limited to 40 hydrogens. So if we're operating under this assumption that it is oxygen, we then have to move around the H count and the oxygen count to fit into the total that is 60.
So the carbon number is exact and won't change?
So
So from the 19 carbons, we figured out there was the 228 mass contribution. That left us with the 60. That has to be hydrogen plus the heteroatom. The maximum number of hydrogens was 40. We had 20 remaining. So we're operating under this assumption that the heteroatom is oxygen. And we know that its atomic mass is 16. So we're dealing with 1 for hydrogen, 16 for oxygen. We need to find some ratio that fits into 60. Because oxygen is the higher mass, we're going to run through this table by increasing its count from 1. So basically, if you look at, multiplying across for each row, those combinations will end up giving you 60. So in terms of the ratios, what would make sense? And let me just kick this off by saying we have to get to 60. If we had 1 oxygen, that would be 16 mass units. We'd then have to have 44 hydrogens. So 16 plus 44 is 60. But this is wrong, right? Because the maximum number of hydrogens is 40. So that makes no sense. Choice D also makes no sense, because if we had 4 oxygens, then we would have to have negative number of hydrogens, and we can't do that. So it's got to be either B or C here. So that's what I mean by getting the math to equal that. So from that, we have two molecular formula claims. So C19H28O2, C19H12O3. So they're both valid. They now equal the 288. But what could we do to further increase our confidence of one over the other? I would say calculate the degrees of unsaturation. So if we did that for both of these, how many degrees would choice B have? 6. So again, there's a maximum of 40 hydrogens. Subtract out the 28. That gives us 12. Divide by 2. That gives us the 6. So what about for choice C? So 40 minus 12. That gets us 28. Divided by 2, that's 14. So even though both molecular formulas are valid, the one with 14 degrees of unsaturation should throw up a red flag in your mind, because that's a lot of degrees of unsaturation for that number of carbons. So for this one, B is the best ratio. And yeah,
At what number of degrees of unsaturation should the red flag start going off? Like how high should we allow it to get?
so there's a couple of them you kind of want to maybe memorize, for lack of a better word. 4 is a good one because 4 is typically a benzene ring. So a benzene ring has 3 pi bonds, 1 ring, that's 4. So that's kind of normal. If you look at, there's 6 carbons there. When you start, getting higher and higher with a very small number of carbons, then it should be a red flag. Because you're going to have to start putting those carbons into rings or double bonds that might be strained. And when I talk about strain, that's more of like module 3 stuff. But the test of this, the practice to learn it is try to draw something, with a lot of degrees of unsaturation and a small carbon count. In I think the prior example on Monday, this is like C7H2. That had like 7 degrees of unsaturation. I figured out a claim I could draw for that, but structurally it wouldn't make sense because there's just a lot of strain in it. What? Say it again.
Like 3 carbons, but they're in a ring and they're all double bonds. Is that even possible?
3 carbons in a ring, you can do that. All double bonds. It might be plausible, but again, with ring strain and things like that, you could probably rule it out as like physically existing. So in our rundown here of looking at these possibilities, what was the most reasonable? 2 oxygens, because then we have a reasonable amount of degrees of unsaturation to work with. We're not having to put things in that might not be structurally sound based on bond angles and hybridization. So hopefully you're still with me at the end of this little journey here on testosterone, in understanding that from that molecular ion 288, we were able to come up with that molecular formula. And again, through that, we did have to make some assumptions about the heteroatoms present. And really the ambiguity was, is it oxygen? Can we run with that? So based on the parent being even, we kind of ruled out nitrogen. We looked at this, again, M+2% to rule out chlorine and bromine. See that the M+1% here? That will always be present because of the C13 isotope. You're always going to have that. The reason this molecule has a signal at M+2, because you have a lot of carbons, you're increasing the possibility that a molecule has more than one C13 in it. That's this statistics of that 1.1% abundance. So the next set of data we see here we're gonna dial it back to simpler functional groups, but now notice there's no structure shown. You're just given mass data. So we want to go through this and start making some claims to structures that will fit this, and then that's going to lead us into the IR. So here's the information we're given that I just rewrote in a tabular form. So the parent ion has a mass of 72 and an abundance of 100. The M+1, which is at 73, has an abundance of 4.3%. So what can we start claiming about this? We know there's C, we know there's H. The mass is even, so we're going to assume that there's no odd number of nitrogens. There's no M+2 data given. So therefore, there's no chlorine, there's no bromine.
Could you repeat that one?
So in the data you're given, see how it's M and then M+1? There's no M+2. If you start seeing major signals for M+2 that are in that 1-to-1 or 3-to-1 ratio, those are indicative of chlorine or bromine. So given that data, which heteroatom is most likely present? So we're going to run with oxygen again. So we rolled out N, Cl, and Br.
From that data, does it have to have an oxygen in it, or could it just be carbon hydrogen?
It could be just carbon, hydrogen. So again, for this equation, we're going to plug in those percents. So the 104.3. So when we do that, the exact number of carbons will be what?
3.9.
So 3.9, we're going to use 4. So that's the next thing we should do is just take that number, multiply it by 12. That takes care of the carbon contribution. So now what about everything else? Can you run through that sort of same logic we did for testosterone and figure out the H and O ratios? I think we can eliminate A, because the maximum number of hydrogens for 4 carbons would be 10. We can eliminate D. And then B and C both have 1 oxygen. So really what you're figuring out now is the H count. So which one of those H counts is going to get us to that mass of 72? So C will be the right answer. So we're given, or we found C4H8O. Oxygen doesn't affect the hydrogen count. So we get down to C4H8. For 4 carbons, the max number of hydrogens is 10. So within that molecular formula, there's 1 degree of unsaturation. And a degree of unsaturation is a pi bond or a ring. And so this is where things start to spice up a little bit with the presence of that heteroatom. So of your functional groups with pi bonds and rings, now you have to consider including the oxygen in there. And so that's why you want to start, having a good idea of, what is a carbonyl group, what is an ether, what is an alcohol, that sort of thing. So C4H8O with 1 degree of unsaturation. Of the possible functional groups listed, which one cannot be present? So I've heard C, ester. I see a hand symbol. So ester, why not? Requires 2 oxygens. So again, that's part of the intuition that we need to develop of what the molecular formula and degrees of unsaturation are telling us. So you don't want to have 4 carbons and draw an ester because, again, the metacognition should tell you that that's wrong because you've included an extra oxygen in there. So A, B, and D here are possible functional groups within that molecular formula. So let's just practice drawing them. What are they? So a ketone has a carbonyl, which is a CO pi bond, and that has to be internal to the chain. So there's 4 carbons, and I'm going to put the carbonyl there. So that's a ketone. So maybe above the name here, I'll just draw that to show where the degree of unsaturation is. So B has alcohol and cycloalkane. So alcohol has to be OH, so that takes care of the oxygen. So the degree of unsaturation is in a ring. And we'll just draw the biggest ring we can, so a 4-membered ring. Then we bond those things together. So that could be a claim. And then for the aldehyde, the degree of unsaturation is in the carbonyl, but now that is at the end of the chain. So we were able to use that mass spec data to arrive at a molecular formula, determine the degrees of unsaturation. From that criteria, knowing where to assign the degree of unsaturation, knowing what functional groups oxygen has, we made some claims. But you see there's these three shown. We could probably draw another one here with a smaller ring that's still an alcohol. So we have all these different claims. How do we know what one is real based on some data that we would see? So A and D both have carbonyls. This one has an alcohol, so that differentiates them somewhat. Of the carbonyls, this one has a carbon and a carbon. This one has hydrogen and carbon. That subtle difference is actually a diagnostic signature in IR. So even though they both have carbonyls, that little bit of variation, if you're looking in the right spots, it'll tell you the molecule has an aldehyde in it, or if it doesn't have the specific signature, it's got to be a ketone. And so then you can narrow down from the possibilities of carbonyl versus alcohol to one sort of functional group. And so how do we end up doing that? So infrared spectroscopy is one of the main methods that tells us, okay, this functional group is present. It's not telling you about like the overall connectivity of the entire molecule, just little bits and pieces of it. But if you're able to extract that data from it, like we said before, an ester has to have 2 oxygens. So when you look at IR and you see a specific signal, you can say, I'm confident that signal belongs to an ester. Therefore, the molecular formula has to have 2 oxygens and at least 1 degree of unsaturation. And so you know that that's the bonding pattern for an ester. And then I need to figure out what's the other stuff bonded here and here. And then bit by bit, you can put these fragments together to propose a structure. So notice that, again, the name changed from mass spectrometry to spectroscopy. And so IR and NMR deal with spectroscopy, and that's the interaction of light with matter. So we'll look at the electromagnetic spectrum, the wavelengths of light, the energy of those wavelengths and what they're doing specifically to the elements or atoms in a molecule. So IR spectroscopy is specifically used to identify functional groups. So again, remember those names, the bonding patterns, the elements required. And practically speaking, the way this works is the IR light is interacting with a bond dipole. So say we have an alcohol where R is the rest of the molecule. So alcohol is the OH bonding pattern. We know from electronegativity and the fact that oxygen has lone pairs that oxygen's delta minus, hydrogen's delta plus. So by assigning that partial charge, we can then write a dipole, so a dipole moment. So that would be a bond dipole. And it's a permanent dipole because that's a covalent bond. So what the energy of the IR light will do is interact with that. So you have a sample, it's in an instrument, you're shining this light on it, and out the other end is a detector. So I'm going to give you just the basics of that. We're not going to go too much into the math or anything. But the fact that the IR light does that and the instrument, quote unquote, sees it, allows us to see it and interpret it. So you have a stimulus and a response. The important thing to note is when you see a signal in IR, there has to be a dipole moment. And that can get pretty tricky when you're dealing with, again, specific type of carbon-carbon bonds, single, double, and triple. You don't always see them because if two of the same element, they have the same electronegativity, the magnitude of the bond dipole is not that great. So getting back to that data we had, '72, we came up with C4H8O. We came up with some structures. We want to start, if we're given a piece of data, can we start ruling some things out and then possibly considering a smaller set of possibilities? This is an IR spectrum. I would hope that we all can agree on this, even in these turbulent times. This spectrum looks nothing like a mass spectrum. So that's part of the recognition here is when you see a piece of data, know where it's coming from. So on the infrared spectrum, you have the x-axis. The units for this are kind of weird. They're called wave numbers. And it's typically reported in reciprocal centimeters. That deals with sort of the wavelength of IR light normalized to a certain unit. So that's the x-axis runs from 4,000 on the left to about 500 on the right. The y-axis is percent transmittance. So from 0 on the bottom to 100 on the top. We're not going to talk too much about, do you remember Beer's law from Gen Chem? A little bit. So there's two terms, transmittance and absorbance. They're inverse to one another. Maybe I don't have my fancy laser pointer, but I have this cat chasing red one that barely works. So I'm pushing that button, right? You see the red dot? That's 100% transmittance. Now, when I put my hand in front of it, you don't see it on the wall anymore, right? So that's, if the wall is the detector, this is 100% transmittance. Now it's 0%. Alternatively, this is 100% absorbance. So when you're reading these at 100%, all of the light is going through the sample. There's nothing in the molecule that's absorbing any of that light. So you don't see any signal. So I'm going to cheap out and say there's nothing being absorbed. Then you hit this point where it starts to dip down. And so something's being absorbed. There's some energy, light being absorbed. So this stuff right here, that's a signal. So as we progress back up this jagged stuff, notice that it starts going back up here, and we could call that the baseline. And then there's nothing. Then it hits this other thing, it starts going down. That's another signal. So we go through there, boop, go back up. And IR can get overwhelmingly complicated. So for this class, anything that's below that number here, 1500, I'm just going to tell you to ignore. We're not going to get into the weeds and say, okay, what is this little blip due to? That's beyond what we need to know. So from 4,000 to 1,500, we're going to look in specific areas. For lack of a better way of teaching this, you're looking for the shape of that signal. The functional groups will have a unique shape in certain regions. This one that I've highlighted here at 1730 wave numbers, that is due to a CO double bond stretch. So that's what it looks like. I would say that's an intense signal because from this distance here to that distance is pretty tiny, meaning that the light is strongly absorbing in there. Like, see this little blip here? Don't drive yourself nuts trying to figure out what that is, because from 0% up to there, it's not really absorbing much. So it's not worth trying to figure out. So we want to look at these intense signals. What's the shape of them? And a lot of these functional groups will have like a unique shape. So they're not normal looking shapes like a box or a sphere or anything, but you can sort of tell if it's got an alcohol, it looks like this, therefore OH is present. So if I say 1730 is a carbonyl, we drew some structural claims that had carbonyls. Another one we had OH. So given this spectrum, because that signal is present, there has to be a carbonyl, which means the OH is not present. And the OH occurs in another part of the spectrum, and it looks very different. I mean, it sticks out like a sore thumb. So when I look at this, I know it's not there, and I can say, okay, the molecule is not an alcohol. So to set the stage for interpreting this, before we go too much further into the actual spectra, let's just review the different functional groups to see what are the general patterns and what regions do they occur in. So which functional groups have that relationship? A heteroatom bonded to hydrogen. What? So D. A is eliminated because of the ester. B, the tertiary amine. C, the tertiary amide. So again, those words translate into that bonding pattern that match this criteria of XH. So what functional groups have a triple bond? So A, so an alkyne and a nitrile. What functional groups have a carbonyl, CO double bond? C. A is out, a nitrile is a triple bond. B is out, that's OH. And then D is out because amine is NH. So this says what has a carbonyl then bonded to an extra heteroatom, extra oxygen. A is out. The heteroatom there is nitrogen. C is out because that's chlorine. And then D is out because we already kicked out amide. So the answer here is B. So that's the anhydride, the acid, and then the ester. So that's kind of the minimum stuff you need. The things I left open can be bonded to whatever. So now this one was carbonyl bonded to nitrogen. And based on the prior problem, this has to be the amide. So as we learned in Module 1, there's a lot of ways of communicating functional groups. So given the word of the functional group, what line or condensed formula represents that? So we have alcohol, amine, and carboxylic acid. So alcohol, that's our OH, amine, NH2, that would be primary, and then CO2H. So again, from that word alcohol, you're focused on OH. Amine, NH2, NH, or N, based on its class. Acid, CO2H. Where we're going with this, you're looking at the word, the minimum elements in the bonding pattern of the functional group, and then you're going to associate that with a pattern in the IR. So amide, alkyl chloride, and acid chloride. So this one is A. So amide has the carbonyl bonded to nitrogen. Alkyl chloride is just your average old carbon. Acid chloride has a carbonyl bonded to the chlorine. So as I said, what's the point of this? Of all of those questions, we were looking at kind of in order of reading the IR, single, triple, double bonds. From left to right, from 4,000 to 1,500, as you interpret the IR, that's the three regions those things occur in. Your CH, NH, OH, that's in one region. Triple bonds are in region 2. And then double bonds, CC, CO, are in region 3. Anything below 1,500, we're not going to study, because these are the main bonding patterns in those functional groups. So when you're looking at IR, you look to these regions, do you see the presence of a signal that will confirm the functional group? Then you can say, yeah, this is a fragment in there. If it's not there, then don't propose it, because it's not being supported by the data. So visually, here are those regions. The different functional group names. Region 1, XH stretching, where X is carbon, oxygen, or nitrogen. So we can see the different types of hybridized carbon H stretching, amines, alcohols. I'll tell you one thing. Every molecule has sp3 hybridized carbon H stretching, so that's not diagnostic for anything. You're always going to see that. So it's not really telling you anything you don't already know. NH and OH stretching look very different. We move into another part of the spectrum. There's our triple bonds, nitrile and alkyne. I do want to point out something here. It's got to be a terminal alkyne to see that stretch. An internal alkyne, even though it has the triple bond, the reason you won't see the stretch is because the dipole moment is not very big.
Aren't those two the same? The one to the left, both of the
Yeah, these are the same. What this region is showing you is this stretch, CH, and then what this region is showing you is the CC.
So if it was that alpine, it would have a peak in both region 1 and region 2?
Yes.
Okay.
And so that's one of those pairs you have to look for. If you have an internal alkyne, you're not going to see it because the bond dipole is small and the intensity of this signal won't be picked up by the instrument. So we saw a lot of functional groups with carbonyls, right? Aldehyde, ketone, acid, ester, and hydride, acid, chloride, and amides. If all of the CO pi bond stretching looked the same, we would be kind of screwed, because then you could make a lot of assumptions about which one of those functional groups is present. But fortunately for us, whatever is bonded to that carbonyl affects the way it looks and some subtle differences in where it occurs on the x-axis. So those are the three regions we look to confirm the presence or absence of those bonding patterns. So just a brief kind of introduction to the electromagnetic spectrum, specifically IR. So I guess the more scientific term for light is the electromagnetic spectrum. And again, there's two things in there, electricity and magnetism, which is like what, physics 2 or something. So light has two vectors associated with it, an electric vector and a magnetic vector that run perpendicular to one another as light propagates through space. When light moves through space and then it interacts with matter, it will affect that in different ways. So that's a stimulus. What it does is then a response that is measured by an instrument. So on the spectrum, at the low energy side, longer wavelengths, there's radio waves. And radio waves are used for NMR. They affect the nuclear spin. As the wavelength gets shorter, the energy goes up a little bit. Now we're into microwaves, and that says rotational motion. So why does your bag of popcorn pop when you put it in the microwave? What is it doing? It's heating the water that's present in the popcorn kernel. So the water gets hot, it turns to steam, and then it pops. So the microwaves, what they're doing is affecting the rotation of the water molecules. It's adding kinetic energy. From there, we get into infra. So infra means before, infrared. So you see red in the visible region. This is the colors we see visible. So infrared is before red. IR light affects a bond dipole. And so I'll just give you a crappy demonstration on the next slide of what that is. Color is something we'll talk about in organic too. Why are molecules perceived to have color? What functional groups give them color? How do humans see that? So that's a different set of functional groups, a different interaction of light with molecules. You've heard about UV. My advice, wear sunscreen, if you've ever heard that. So UV light can cause skin damage. It's higher energy now. The wavelength is shorter. Then we get up into the heavy hitters, X-ray, cosmic, and gamma rays. So all of these different forms of light interact with matter, and as humans, we use them for imaging. So we got about 2 minutes left. We'll just show a brief thing with Bob Ross here. What is a bond, and why does IR work? We know a bond is an attraction between two atoms, right? This is a curve you'll see a lot, and if you go on to more chemistry courses, if you have two atoms that exist but are unaware of each other. If you look at the x-axis, that's the distance between these two things. So as the distance closes, they get closer and closer. So there's that attraction from electrons to the nucleus. And then finally they get so close they're in a well. So it's like, boom, they're in a well. But they can actually, you can squeeze them together that the energy starts going back up, and then it's not stable. So the reason that's a well, see how it says average bond distance, average bond energy? When we report those things, we're measuring from the center here to the center here is the average. But even at absolute zero, there is energy. 0 point energy. Everything's always moving. So when that bond forms, it's not static. It's moving like that, like a spring. So when there's a dipole between them, based on electronegativity or whatever, it's still moving. So when the IR light hits that, it's stretching it back and forth. And then the detector of the instrument sees that as a response. And based on what this is and this is, there are different functional groups. That's why you see them in different regions. So next week we'll talk about what those stretches are, where they occur, but please look at that announcement I sent about the PowerPoint of the different functional groups. So you